Welcome to this explainer. Today, we're diving into something absolutely crucial. We're going to explore exactly how high-level concepts get transformed into actual production-ready blueprints for a massive hospital information system. It's time to unpack how these giant digital systems really work under the hood. So, whether you're an architect, a software engineer, or honestly just someone fascinated by digital infrastructure, you are totally in the right place. Let's get into it. To kick things off, I want you to picture this for a second. Imagine handing the exact same high-level design, a beautifully drawn high-level diagram of a hospital system, to 10 different software engineers. You hand over the design, wish them luck, and check back in 3 months to see what they've built. What do you honestly think you'd find? Well, you'd get exactly 10 completely different implementations. Seriously. Now, a couple of them might actually be highly secure and perfectly scalable. But the rest, they'd probably turn into massive technical debt before they even make it to production. And that's because without hyper-specific, detailed blueprints, engineers are forced to make their own assumptions. And in a critical, high-stakes environment like healthcare, assumptions are incredibly dangerous. To keep us from falling into that exact trap, here's our roadmap for today. We'll cover the high-level design trap, unpack low-level design, unbox the appointment service, trace a system request, dive into enterprise security and reliability, and then wrap it all up with some common mistakes and best practices. All right, starting off with Section 1, the high-level design trap. Let's clarify why relying on just a high-level sketch is basically asking for trouble. This right here perfectly captures the issue. A high-level design, or HLD, really only gives you the broad strokes of what you're building. It's great for saying, hey, we need a patient service and a billing service. But a low-level design, that dictates exactly how you build it. Think of it like this. HLD is the pretty sketch of a new house, while the LLD is the hardcore architectural blueprint that tells the plumbers and the electricians exactly where every single pipe and wire needs to go.
Moving right along to Section 2, unpacking low-level design. Let's formally define what this blueprint actually looks like in the real world.
So, what are we really talking about here? Well, experienced architects spend a massive amount of time sweating the details in these low-level design documents to ensure there are absolutely zero misunderstandings before anyone writes a single line of code. A solid LLD literally leaves no room for guesswork. It explicitly guides the developers, the DevOps engineers, and the QA teams so that everyone is rowing in the exact same direction.
Which brings us to Section 3, unboxing the appointment service. Let's take these concepts and apply them to a real, core piece of our hospital system. When you crack open this service, you better not find a jumbled mess of spaghetti code, right? We need strict, structured internal components. By dividing the service into clear layers, like dedicating a repository layer purely for talking to the database and an API layer just for external communication, we establish hard boundaries. We're totally isolating the business logic. And this intentional separation is a game changer for maintainability, because it means a quick update to your database logic isn't going to accidentally break your API. Now, for the outside world to actually talk to this service, we have to lay down some serious ground rules. We're talking rock-solid enterprise APIs. Yes, we need clear endpoints to book, update, or cancel an appointment. But it's way more than just endpoints. It requires strict HTTP methods, rigorous request validation, and super consistent status codes. We also absolutely have to design for idempotency. That's just the fancy way of saying if a user gets impatient and double-clicks book appointment, the system is smart enough not to schedule them for 2 concurrent visits. In healthcare, consistency is non-negotiable. But what happens when this service needs to talk to other parts of the hospital? We have to make a really deliberate choice between synchronous REST APIs and asynchronous messaging based on our real-time needs. For instance, if a patient is staring at their screen waiting to see if a doctor is available, that has to be a synchronous, real-time HTTP call. But sending out an email confirmation, no way should that hold up the booking process. That gets dropped into a message queue to be handled asynchronously in the background. Diving even deeper inside the service, our database interaction layer defines how we safely handle reading and writing data. In a hospital, data integrity isn't just a nice-to-have, it's literally everything. So we have to define our transactions and implement things like optimistic locking. That stops a complete disaster if, say, 2 receptionists try to edit the exact same patient file at the exact same time. We also map out caching strategies and connection pooling to keep the whole system lightning fast while protecting that sensitive data.
All right, on to Section 4, tracing a system request.
Let's actually trace how this entire architecture functions when a patient tries to book a visit.
Let's follow the life cycle of a request like a story. The patient clicks book on the front end. From there, the data travels securely through our API gateway, passes authentication, and lands at the appointment service. The service immediately does a synchronous check to see if the doctor is actually free. Once he gets the green light, it updates the database and then fires off asynchronous triggers to our audit and notification services. Seeing it mapped out step by step like this in the LLD is exactly how we prove our theoretical architecture will actually work in the wild.
Which leads us perfectly into Section 5, Enterprise Security and Reliability. Because with critical health data, you absolutely cannot just bolt this stuff on at the end.
This is where a lot of teams mess up. Notice how enterprise security mechanisms, like role-based access control and secrets management, are actually living inside every single service here. It's a huge mistake to rely entirely on your API gateway to act as a bouncer for your whole system. In a true enterprise design, we apply the principle of least privilege everywhere. The appointment service itself needs to verify, hey, does the user asking for this data actually have the right to see it?
And let's be real, things are going to break. It's inevitable. So to stop a tiny glitch, like the billing system going offline for a minute, from taking down the entire hospital, we need a robust error handling strategy. This means using circuit breakers to instantly stop sending traffic to a failing service and using dead letter queues to safely store failed messages so we can process them later. We are designing for graceful degradation. If one minor feature breaks, the rest of the hospital keeps running smoothly.
A massive part of reliability is actually knowing what's happening under the hood. Observability has to be built in from day one, not treated as an afterthought. Every single service is designed to output structured logs, metrics, and correlation IDs. Think of a correlation ID as a tracking number for a package. It lets us trace a single user's request across 20 different microservices so we can find exactly where an error happened. All of this feeds straight into our centralized dashboards and alerts.
And hey, a great low-level design is also a total game changer for your DevOps team. It spells out exactly how we're containerizing everything with Docker and Kubernetes, how environment variables are managed, and it defines the deployment automation rules. Setting up things like readiness and liveness probes tells Kubernetes exactly how to check if our deployment service is healthy and actually ready to handle real patient traffic.
Time for our final segment, Section 6, Mistakes and Best Practices. Let's look at the biggest architectural potholes you need to dodge when it's time to code. You'd be amazed how often project teams accidentally sabotage their own architecture. They build these tightly coupled fat services that try to do way too much. They pair that with hard-coded configurations that you literally can't update without taking the whole system down. They skip transaction management and build massive, unwieldy APIs. Doing this completely defeats the purpose of microservices, and it just leaves you stuck with a distributed monolith that is an absolute nightmare to maintain.
If you remember only one thing from this explainer, make it this. High-level design defines the architecture, sure, but low-level design? That defines the execution. Taking the time to craft a precise, thoughtful LLD is the secret sauce that actually speeds up development, simplifies your testing, and guarantees your system can scale. An architecture only really succeeds when every little detail has been intentionally designed.
So, okay, your application layer is structurally sound now. But before we jump into our next explainer on database design, I want you to really think about this. How exactly will your data architecture survive 1 million concurrent healthcare records? We'll tackle that critical question next time. Thanks so much for learning with me today.